Hello and welcome back to another Math 112 lecture. Today we are going to look at how our trigonometric relations can help us with non-right triangles. I'm going to do this well, let's start with an example. Let's talk about why we want to know how to do this. Suppose we've got two radar stations located 20 miles apart, and they detect something in the sky between them. And the one radar station detects this object at an inclination of 15 degrees. The other radar station detects this object at an inclination of 35 degrees. The question is, how high up is this object? The answer is we can get there, but we can't get there with what we currently know. We need to look at something called the law of sines. What the law of sines tells us is that the ratio between the side of an angle and the length of the side opposite that angle is equal all the way around a triangle. So the sine of angle alpha divided by the length of side A opposite that angle is equal to the sine of angle beta divided by the length of side B, which is also equal to the sine of angle gamma divided by the length of side C. The law of sines will help us anytime we know two angles and a side, two angles and a side, or two sides and an angle, as long as the angle is not included between the two sides. It gets a little hairy in that case. And in that case, we usually go to the law of cosines. The law of cosines is kind of like a generalized Pythagorean law. And what this says is this: you can relate the squares of the lengths of the sides of the triangle to one another, as long as you include one cosine. So here's what we do. The length of side A squared is equal to the sums of the squares of the lengths of the other two sides minus 2 times the product of the lengths of those other two sides times the cosine of the angle opposite the side we care about. If you can memorize this pattern, it will help you to build the law of cosines in the way that you need it. So let's go back to our radar station problem. Let's take another look at this, now armed with the law of sines. And here's what we know. We know the length of the side of the distance between the two angles, which is the length of the side opposite this angle gamma. What we really care about is the height. We're going to label this side A, which makes this guy over here alpha. I'm going to label this side B, which makes this guy over here, this 15-degree angle, my beta. And that leaves my 20 miles as C. So we know something about triangles. We know that if we add up the three angles in this triangle, we have to get 180 degrees, which means then that gamma is equal to 180 minus 15 minus 35, or 130 degrees. Now we've got everything we need. Let's go ahead and find side A. So what we're going to write is we're going to write the sine of gamma divided by the side opposite that side, the length of the side opposite that angle, is equal to the sine of angle alpha divided by the length of the side opposite that angle. So let's fill in what we know. We know the sine, we've got sine of 130 degrees divided by 20 miles is equal to the sine of 35 degrees divided by the length of side A. We do a little algebra to solve that, and we end up with A equals 14.975 miles. All right, we are almost there, because we also know that the sine of this angle beta is equal to the height, or the length of the side opposite that angle, divided by the hypotenuse. And if we consider just this little right triangle here, this right triangle on the left, we can write that the sine of 15 degrees is equal to h over a, which means that the sine of 50, so that means we can find h, which is going to be a times the sine of 15 degrees. We already found a, so h is 14.975 times the sine of 15 degrees. Find the sine of 15 degrees on your calculator, and you will get the result that our unidentified flying object is moving at about 3.876 miles above the surface of the Earth. All right. So let's just apply the law of sines in a few different cases. So here's what we know. The longest side of this triangle has length 10. And one of the adjacent angles has measure 30. We're going to call that angle alpha. And then it just says, find the other angles if the side opposite the 30-degree angle has a length of, and then we've got three different cases. So let's start with case A. In this first case, we're saying that A equals 3. And we want to find the other two angles. Well, that's not so hard. Sine of gamma divided by 10 is going to equal the sine of alpha, which is 30 degrees, divided by 3. Okay, the sine of 30 degrees, that's one we know. The sine of 30 degrees is 1/2. So what this means is that the sine of gamma is going to be 10 times 1/2 divided by 3, which is 5/3. Wait a minute. This is an unadulterated sine function. What's the range of the unadulterated sine function? -1 to 1. This is not possible. That means there is no such triangle. So this triangle, where we've got one side that is 10 inches and this side that is, this angle that is 30 degrees, and this side at 3 inches, doesn't exist, can't do it, it's not physically possible. That will happen. Not every desired geometric relation is possible. We know that, right? Okay. Let's look at problem B, where this side A is 5. We're going to set up pretty much the same thing. So this is for B. Sine of gamma divided by 10 equals sine of 30 divided by 5. We still know the sine of 30 degrees is 1/2. So that means that the sine of gamma is 10 times 1/2 divided by 5. 10 times 1/2 is 5. Divided by 5 is 1. So now we think about what angle in the first or second quadrant has got a sine equal to 1. And we recall that that would be 90 degrees. So in this case, gamma equals 90 degrees. We can use the fact that our angles have to add up to 180 to find that this is a 30, 60, 90 degree triangle. Okay? All right, let's try problem C. And same thing again, we're going to set up that the sine of gamma divided by the length of the side opposite that angle is equal to the sine of 30 degrees, divided by the length of the side opposite that angle. In this case, that length is 6. Which means that the sine of gamma is equal to 10 times the sine of 30 degrees, which is 1/2, divided by 6, which is 5/6. Now, if we take out our calculator, so what that means is that gamma is equal to the inverse sine of 5/6. If we take out our calculator and we plug in inverse sine of 5/6, we will get that gamma equals 56.4, 4 degrees. But if we look carefully at our circle, we will know that by symmetry there is another angle in the second quadrant where gamma that also has sine of 5/6, and that is the angle 123.56 degrees. That's okay. Sometimes we can have two possible triangles, and it depends on whether we're looking for this triangle or that triangle. This one corresponds to this angle, or that case. This one corresponds to that case. Both of them will satisfy our given conditions. So we just report both of them as possible. What this means is that we've got two possibilities. We can either have so if gamma is 56.44 degrees, that means my third angle beta is 93.56 degrees. And if my gamma is 123.56 degrees, that means my third angle beta is 26.44 degrees. This is an ambiguous solution, but both solutions are possible. Okay, option D. Set this up again exactly the same way. Sine of gamma divided by 10 is equal to the sine of 30 degrees divided by 12, which means sine gamma equals 10 times 1/2 divided by 12. So the sine of gamma is equal to 5/12. Take a look at our circle or our graph or our calculator, And we find that my angle is 24.62 degrees. Now, there is by symmetry another angle that would have this same sign. And we would get that by subtracting this angle from 180 degrees. I want you to think about why that second angle is not a solution that we need to worry about. If you can't figure out why I'm not considering, I'll tell you. If we take the 180 minus 24, hold on, I gotta do this. I did it earlier. So 180 minus 24.62, we get an angle of 155. That would mean my gamma is 155 degrees. I'd find beta by adding 30 to 155 and subtracting from 180. I get a negative angle. That doesn't make any sense. So you're not always going to get two possible solutions. And you'll know it, you'll see it when you go to add up your angles and you realize there's no possible way to make a sum of three angles that makes 180 degrees. You can kick out the second solution. So we're just going to keep the 24. So if I add 24 to 24.62 to 30 and then subtract 180 or subtract from 180, we get that the third angle is 125.38 degrees. And we could go ahead and find the lengths of the sides here, either using for any of these three cases, either using the law of sines or the law of cosines. What I wanted to show you here was that we can get come across situations where there is no physically possible solution, where there is exactly one mathematically possible solution, and that only happens when one of the angles is 90 degrees. Where there are two possible solutions, and they're both two mathematically possible and physically possible solutions. Or we can get into a situation where we've got two strictly mathematically possible solutions, except that it would require a negative angle. And so we know that that's not physically possible. So we end up with only one physically possible solution. And that is the only one that we will report. Okay, so let's look at this example. This is actually not an unrealistic situation. Someone goes walking and they walk 10 miles east, and then they turn 30 degrees north. So we've got an angle right here of 30 degrees. We know that this is 10 miles. And then they walk another 5 miles. Clearly my triangle is not to scale. Sorry. But how far must they walk to head home? So we're looking for this distance C. My known angle gamma, which is 150 degrees, is included between my two known sides. The law of sines will not help us very much here. So we're going to use the law of cosines. And recall that the law of cosines, so we care about C, side C, so I'm going to write the law of cosines in that form. So the law of cosines tells us that C squared is equal to A squared plus B squared minus 2AB times the cosine of my angle opposite my side C. So C squared in this case is going to be A squared, which we'll call 10, plus B squared, which we'll call 5, minus 2 times 10 times 5 times the cosine of my 150 degrees. Okay, so I've got here 100 plus 25 is 125 minus 100 times the cosine of 150 degrees. So 150 degrees cosine we have to be a little bit careful because that actually gave us a negative number. But that's okay. And I get c squared equals, 211.6. So let's take the square root of that. And I get 14 miles. Do a quick check to see if I think that makes sense. And yeah, I think it does. The straight line distance between any 2 points should be shorter than the distance it took to get there through 2 legs. So yeah. Okay, not too hard. We can also use the law of cosines and a combination of the law of cosines and sines maybe to help us find the area of a triangle with side lengths 7, 8, with the area of a triangle where we only know the side lengths. So let's talk about this. We've got this triangle. Lengths 7, 8, and 9. Remember that the area of a triangle is 1/2 the base times the height. But the height has to be this vertical, right? And this 9 would then be the base. Well, fiddle faddle. But that's okay because we can do this. Let's label this angle alpha. That would mean this guy is side A. And the law of cosine tells us that a squared is equal to b squared plus c squared minus 2 times b times c times the cosine of the angle opposite side A, which we'll call alpha. So for this triangle, that means that a squared, 7 squared, is equal to 8 squared plus 9 squared minus 2 times 8 times 9 times the cosine of this angle alpha. What we're doing is we're finding this angle. We're going to find this angle so that we can then use the sine of this angle to find the height. So 49 is going to equal 64 plus 81 minus 2 times 72 is going to be 144 times the cosine of my angle alpha. Let's do a little algebra here. And so we're going to take 49 minus 64 minus 81 and divide that by negative 144. And we get that 0.6667 equals the cosine of my angle alpha. Give me a second. This is a different calculator. I'm not quite sure how to, there it is. So take the inverse cosine And we get that my angle is 48.2 degrees. Or we could get another angle that was 132 degrees, but so let's just, but that would give us a weird, well, that's okay. Let's see what happens. Or 131.8 degrees. So what we're looking at is this would be, the 48.2 would be this angle, or this triangle. Let's see. This guy with, again, so this is how we check. So this would be the 7, the 8, and the 9. Does that make any sense? Now, the longest side is going to have to be opposite the biggest angle, probably. Maybe not. No, this should work. Okay. Yeah. So this would then be our height. Okay. This is this case. Now, see, that doesn't make any sense. Because if we've got this angle, this big fat angle in my triangle, then my 7 cannot be opposite that one. So we can throw this guy out. Again, we're going to get some mathematically possible solutions that don't make any sense in the physical world. And we just have to kind of think about it. Okay, so now I've got my angle of 48.2 degrees. I can find my height because my height is given by the sine of my angle divided by the hypotenuse of this right triangle, which would be 8. So height take the sine of that angle and multiply it by 8. And we get that our height is about 5.96. So now we can find our area is 1/2 times 9 times 5.96. So this triangle will have area of 26.8 square units, whatever those units might be. And that is all I have for today. We will come back again and talk about section 8.2. Have a great day. Do good math, and I'll see you all again soon.